Let X be a population random variable with an unknown parameter theta, like a mu, for example. Consider simple hypothesis tests, meaning these are simple hypotheses. Null is that theta equals theta sub 0. Alternative is that theta equals theta sub 1. And of course, you would assume theta 0 and theta 1 are different. Otherwise, you wouldn't be doing it. Nobody would ever do it that way. Let vector x be a vector x1 through xn. It's treating that vector as the random sample, which you can do if you want. Of size n, it's assumed from the distribution of x, from the population. Size n used to resolve the hypothesis test. By resolve the hypothesis test, it means make a decision to reject or not. At significance level alpha, meaning you want your type 1 error to be alpha, or maybe even less than alpha. Let C be a rejection region satisfying certain conditions, 3 conditions here. For some positive number k, this ratio is less than or equal to k for all points vectors in the rejection region, greater than k for all points in the complement of the rejection region, and alpha, the probability of C, meaning essentially that the vector x is in C, when the null is true, which does equal this n-tuple integral. There's n integral signs there. If n is 1,000,000, there's 1,000,000 integral signs there. That's just the probability of a type 1 error being in the rejection region, rejecting the null when the null is true. What is L? We said what L is. Okay, the authors are actually assuming you know what L is. L is the likelihood function. Then the test statistic, that's the ratio of these likelihood function values and the rejection region C comprised of all vectors x, so that this is true, constitute a most powerful test at significance level alpha. A most powerful test. So the power is maximized. Beta, probability of type 2 error, is minimized when the power is maximized because the power is 1 minus beta. What in the world? This is really, really confusing. I always had a hard time with this. And like, what is K as well? K could be lots of different things. In fact, K depends on alpha, actually. Different alphas will produce different Ks. The point is essentially that this inequality in number 1 defines the rejection region, the critical region. That's the point for a most powerful test, to maximize the power. The rejection region is a set of points satisfying an inequality like that. And you just have to see how that works out in particular examples. The funny but good thing about this, how it works out in particular examples, is that it confirms what you might say is the obvious. It confirms, for example, when you're doing this kind of test, which effectively is like a right-tailed test because 28 is bigger than 20, that your rejection region should be to the right of some number, not to the left of some number, for example. Or maybe something weird like, oh, to the right of some number plus some other interval in here. Reject if X bar is bigger than 25 or between, say, 22 and 23. Doing weird things like that produces worse results, is the point. So that's good, but maybe you might say it's good but silly. I mean, yes, we want to confirm things that seem like they should be the best things to do, but it's like seems like overkill, right? Why do I need this big long lemma to do that? I'm still exploring it, wondering whether there are surprising results that follow this from this lemma. I'm not an expert in this. I haven't discovered them yet, but maybe there are some unexpected things that follow from this lemma. Maybe especially in higher dimensions, because it's kind of written like with higher dimensional ideas in mind, perhaps. We've got 20 minutes. Let's try to understand this lemma, start to understand it in the context of an example. By the way, people have studied this lemma for their senior seminar project in the past, and they have proved it. The proof is in this book. It involves doing a bunch of integrals. It's actually not as hard as it looks, because you're not actually doing any integrals. You're just thinking about them and using properties of integrals. So even though that looks really hard, it's not as bad as it looks. Why are they doing integrals? Actually, the implicit assumption must be how you have continuous random variables. Likelihood functions with discrete random variables give you actual probabilities. With continuous random variables, we still define them, but they don't give you actual probabilities. You have to integrate them to find probabilities. Talking multivariable calculus, there are joint distributions, multivariable integral. How does this work out in an example? Let's consider our standard, most simple example. In fact, effectively like this example. Maybe we should even do this example, continue this example just to use particular numbers. I could keep n and sigma squared unspecified. And in fact, I could even keep 20 and 28 unspecified. I could call them mu0 and mu1, perhaps. Should I do that? Maybe I should keep these mu0 and mu1, but I'll keep n equals 9 and sigma squared equals 25. So n again still is 9 here. Sigma squared is 25. Null hypothesis, mu is mu sub 0. Alternative hypothesis, mu is mu sub 1. We do want to keep these to be simple hypotheses. And let's say that's equivalent to a right-tailed test. Let's say mu1 is bigger than mu0. Maybe that's why students get so confused about inequalities. We sort of tend to write greater than, more than, less than when we're just talking about inequalities. But less than is maybe a more important thing to focus on when you're thinking about number lines and things on the left being less than things on the right. But here, the bigger things on the left, maybe that's what causes the confusion. What's the goal? What's the goal? The goal is to try to understand the lemma. So if we're going to understand the lemma, we need the likelihood function. Let's say x is normal. Oh boy, this is going to be maybe not so good. For purposes of calculating the likelihood functions, because the PDF of a normal is not so nice. Let's do it anyway. PDF of normal. Instead of writing x, let's write e. X of something is just nice typographical way of writing e to that something. Oh, can I do it from memory? Yeah, okay. L of a general mu. We're thinking of, say, little x1 through little xn as being a fixed observed value of the random variable, observed random sample. We're given. those numbers so that the likelihood function as a product of PDF values is indeed a function of mu. One over square root of 2 pi times sigma. If sigma squared is 25, sigma is 5 times e to the negative x minus mu will be xi minus mu squared over 2 sigma squared, 2 times 25. It is a good idea to simplify this. How? We can factor out this thing as long as we raise it to the nth power. It is a constant. I think I'll put the 5 in front of the square root. And then we can use properties of exponents. I'm not taking the logarithm here. So I'm not doing the log likelihood function. We can use properties of exponents to get rid of the product symbol and write it as e to a certain summation. If you think about it carefully enough, it's negative 1 over 50 times the summation. I goes from 1 to n of xi minus mu squared. Separation here. Right? What am I using there? I'm using the fact that e to the a times e to the b is e to the a times b, or e to a plus b, excuse me. That's what I'm using. Add the exponents. Get rid of the capital pi product symbol. All right, go back to the lemma now. Neyman-Pearson lemma. We need to look at these ratios. With the null value of mu in the numerator plugged into L and the alternative value plugged into the denominator, I'm using mu0 and mu1. I could use particular numbers. I could use 20 and 28, but let's do with the more general case there. The likelihood ratio in the Neyman-Pearson lemma would be L of mu0 divided by L of mu1. It's fortunate that we decided to do the likelihood ratio top to bottom in the same order top to bottom as the null and the alternative. Formula for the top and the bottom is going to be this thing. With the top in place of mu, you'd put mu0. With the bottom, you'd put mu1. Doesn't seem like we're doing much there. Let's go ahead and write it out. Oh, I forgot I specified n to be 9, didn't I? Should we do a general n? Let's do a general n as well. N unspecified. But I am going to keep the variance to be 25. One nice thing about doing the ratio is this crazy thing cancels. And then I've got the ratio of 2 powers of e. I can use another property of exponents. to write that as just e to just 1 power. Where I subtract the bottom exponent, which means I'll get a plus sign. Oops, I forgot my subscripts on the x's, didn't I? Let's put them there. There's what the likelihood ratio simplifies to. Now, it's a little confusing at this point because back up here, I was saying I was given these little x's. So conceptually speaking, I was thinking of them as fixed numbers so that these likelihood functions are functions just of mu. However, in terms of the Neyman-Pearson lemma, another point where it's confusing is when they write it this way, they're not putting the dependence on the x's in there. On the previous page, they just say notationally, for simplicity, well, and even up here, they just call it L of theta. And in here, they're in this integral formula, they're saying L of theta 0, dx1, dx2 through dxn. But wait a minute. How can you integrate with respect to these x's if they're fixed? Well, in this formula, they're not fixed. They're variables. But you don't see that there in that notation. It's a little unfortunate, I think, but is somewhat standard from books I've seen. And also makes it confusing here because what you're really talking about is you're looking for a set of x values that satisfy an inequality like that, where the x's are variables, really. We're after the critical region to be a set of x values that satisfy an inequality like this, where this whole thing is less than or equal to some number k, some positive number k. What we're saying is the critical region takes that form. And it's really a subset. It's really, when you're thinking about it this way, it's a subset of n-dimensional space. Some set of points in n-dimensional space where n could be 1,000,000 or 1,000,000,000 or Google, but most typically we're hoping for smaller n, even 2 or 3, maybe where we could draw the set. We're saying if it satisfies an inequality like that, where k would be determined on out by alpha, that will be a best critical region to use, a most powerful test. It'll maximize the power of the test and minimize the probability of type 2 error. I look at that, I'm like, how in the world can you possibly imagine such a set? Or even compute it? Is it easy to compute? What you do with this is you try to simplify it, this inequality here. First natural thing to do is take the natural log of both sides. Ha, fun. Get rid of the e. Oh, and there's a typo. I forgot my square here. Get rid of the e by taking the natural log of both sides. Natural log is an increasing function, so the inequality will stay the same direction. K is positive, so the natural log of k exists. The natural log of k itself, though, could be negative if k is small. In my mind, I'm going to pretend it's not. I'm going to pretend it's positive. Okay, that's the first step. Can this continue to be simplified? Yes, this is the same as this. Foil that out. Xi squared minus 2 mu 0 xi plus mu 0 squared. And this thing is the same as this. Xi squared minus 2 mu1, not mu0. Xi plus mu1 squared. I could also multiply both sides by 50. I could split these summations into different summations. This one is the same as, this is ultimately because of the commutative property of addition that you can do this. And then the sum of the mu0 squareds is just n times mu0 squared, because mu0 squared is a constant. Something similar with this one. Let me also up here put the times 50. And put negative signs here. Then because of those negative signs, we do get a little cancellation. Like this cancels with that. Could then write ultimately distribute the minus sign through, I get a plus. Okay, these two terms here and here can be combined, and you can factor out a 2, and you can also factor out the summation of the xi's. And being careful about minus signs here, you'd have 2 times mu0 minus mu1 times the summation of the xi's. And then with these two terms, the n can be factored out. Careful about minus signs, you'd have mu1 squared minus mu0 squared. Then we could subtract this from both sides and then divide both sides by this. And a little tricky, mu0, remember mu1 is bigger than mu0. So mu0 minus mu1 is negative. If I divide both sides by that, I have to switch the direction of the inequality. So we're ultimately going to get the sum of the xi's is greater than or equal to 50 natural log of k minus this, minus n times mu1 squared minus mu0 squared, all divided by 2 times mu0 minus mu1. And that's looking pretty simple, right? Sum of the xi's. And if I divide everything by n, I could say x bar, call it little x bar, is greater than or equal to, save time here, all that divided by n. And why not just call that, oh, say capital K? Is it positive? Is capital K positive? That's not so clear. Evidently, it could be positive, so let's not worry about it. But what are we saying here? Remember, the lemma says we're letting C be a rejection region satisfying this inequality. In other words, the ratio of the likelihood functions is less than or equal to sum k for k positive for all values of x in the rejection region. In other words, that inequality defines the rejection region. And for this example, it's equivalent to an inequality like this. X bar is greater than or equal to k. That's a natural thing to do. We just confirm the obvious. Right? Where did my other piece of paper go? We just confirm our rejection region should be everything to the right of some number. We confirm the obvious or natural choice. Well, it's still good that the lemma confirms the obvious. that our most powerful critical region is going to be for this right-tailed test, the region defined by the sample mean being greater than or equal to something. In the lemma, they say k is positive. I mean, if your mu's were negative, very well, your rejection region could be when x bar is bigger than some negative number. So I'm not sure how to quite resolve that. The lemma emphasizes little k is positive. I guess you could resolve it by saying certainly this little k is positive. Yeah, that's probably the way to resolve it. This big K is not necessarily positive. But it's still saying for a right-tailed test, the best critical region to use is when x bar is greater than or equal to something, as opposed to less than something, as opposed to greater than or equal to something over here, and then maybe between, like I said, 22 and 23 here. So it's confirming the natural thing to do. Are there any situations where it confirms something unnatural? I don't know yet. Have a good day.